continue. Perfect. Okay. Welcome back. This is our lecture 19 in high dimensional probability and applications in data science. And it is Friday. And so if you're offline, please take your tea or coffee or something else, like I do, jasmine tea, and enjoy it while we are having this lecture, this conversation. Last class was about Grothendieck's inequality. The proof of it, which is spectacular, is based on one powerful trick. It's called the kernel trick. Remember how the idea was to realize the very nonlinear function, specifically the sine, the trigonometric sine function of the inner product, as the true inner product, but in a different dimension, in a different space. In that sense, we chose not to fight with the nonlinearity as we did in Gemens-Williamson algorithm, not to try to linearize this nonlinearity, but instead of linearizing, we realize that nonlinearity, but in a different dimension. That's very, very, very powerful and useful. It was rediscovered several times, at least after that, in particular in machine learning. And led to the development of the kernel method in machine learning, which is very popular now. Because in this course, I intend to cover some elements of mathematics of machine learning, I thought it would be a good idea now, a good time to introduce some machine learning questions and techniques, and then explain how kernel method, that kind of reminiscent of Grothendieck inequality, enters there. So today we'll start with this will be our first exposure to machine learning from some of you, and we will do this on the simple example, on a concrete example of the problem of binary classification. Machine learning, binary classification. All right. So suppose suppose doctors come to you from the hospital and they say, we would like you to build an automated diagnostic machine. We would like to diagnose, let's say, cancer automatically using a computer. So the patient submits some tests. Test results are maybe cells. You look at the microscope, there are cells. This is your data, and you put, the idea is to put it in this algorithm in the computer, and the computer will give you the diagnosis. Let's say 1 for cancer, and let's say -1 for no cancer. If the computer thinks that the cell is cancerous, a tumor cell, then it would output cancer, and otherwise it would output no cancer. So binary, plus or minus. Now, how do we think about cells? We put it in a numeric form. So let's say each cell has some parameters, let's say D parameters, that the computer can automatically observe. For example, some features of the cell, for example, radius of the cell, perimeter, texture, symmetry, and so on and so forth. Concavity, D parameters. So a cell is a vector. Each cell is a vector in d-dimensional space. So the input is a vector in a d-dimensional space, just a string of parameters. And we would like to find a way of converting that string into diagnosis, plus or minus 1. So we want to find a function that gives the diagnosis f. from RD, from the space of parameters of the cell, to the diagnosis, plus or minus 1. So f of x equals y. So x is, again, the cell, and y is a diagnosis, so the prediction in machine learning terminology, prediction of. Sorry. Okay. Good. Everything is good so far? All right. Problem clear. All right. So machine learning involves the preliminary stage, which is learning, right? How do we actually learn? How do we make the computer learn the diagnosis? For this, we need training data. Well, so the doctors came and asked you, please build this machine, please build this diagnostic machine, and we respond, okay, you give us some training data. You give us a lot of cells that have already been diagnosed. Okay, and we will put this in the computer and let the computer learn from that. So the training data comes in this form: xi, the cells; yi's, the diagnosis. The pairs, they're pairs. So these are n cells that are already diagnosed manually, not by a computer, by professionals, by experts, by doctors. We assume it's a correct classification so that machine then can learn from this experience, from the experience of doctors. So we have a lot of training data. The points that already have diagnosis, already have these labels plus or minus 1. And we would like to find the machine that would learn from that, and for a new cell would diagnose that. Okay, good. All right. So this is what it can look like geometrically in high dimensions. We have points, and some of them are, let's say, cancerous points. Okay, this is +1 points. And some other points have no cancer. Like that. There are -1 points. So each point is, this picture is in dimension D. And what we would like to have is a function that for any other point, let's say if a new patient comes and says, and its point is right there, here, then the computer should say, okay, its point, well, looking at this picture, should have cancer probably, right? Because it's closer to the cancer cells than to the non-cancer cells. And maybe if the cell is here, then the computer should say, okay, this point should definitely should not have cancer, because it is closer to the non-cancerous cells. So the idea here in this picture is so simple, actually. The idea is maybe to separate the cancerous from non-cancerous cells by some interface, and then just assign +1 to the one side of that interface and -1 to the other side of the interface. That's our diagnostic machine, okay? So in this simple regime, we assume, let's assume that the picture is exactly like this. So assume there is linear separation between cancer and no cancer. Doesn't happen in practice, but let's start from this baby assumption that there exists a hyperplane. There exists this hyperplane, a plane in high dimensions that separates this. How do we quantify the hyperplane? It's a level set of a linear functional. So there is some vector, the normal vector, let's say W. So there is the vector that defines this hyperplane, so that, let's say, the hyperplane is a level, so it doesn't matter what level it is. So let's say it's level 1. So I can look at this hyperplane as all points for which this linear function equals some value, let's say 1 for normalization. Okay. And we assume that there is that, so there exists a hyperplane, so that what happens? So that for, let's see, for all cancerous cells, all cancerous cells lie on one side of the hyperplane, and the non-cancerous cells lie on the other side of the hyperplane. That's our assumption. We can write these two inequalities in one, just compactly in one inequality, as one inequality. W xi inner product is, let's multiply it by yi, and it should be always greater than 1. Yes, good. So that's our assumption, that such W exists. Such vector exists. Okay, so if that happens, then we just tell the computer, okay, please find that W, and we're done. So the learning stage of the algorithm is just to find the W that satisfies this. Yeah, good. So far, so good. Everything is clear. Okay, how do you find W? Well, you look at this, and each inequality in here is a linear inequality in W. So it defines some half space, right? If I look at this inequality for a fixed I, it defines a half space in which W must lie. And there's lots of them, there's n of them. So this condition is just the set of all W's here is just the intersection.
I have one small question. Where's the second inner product? It should be less than 1 or less than -1?
Yeah, that's actually a great question. Since we just want to separate them, and we don't care how close these points are to the margin, we just have +1 here and +1 there. So it's greater than 1 on one side, less than 1 on the other side. It just defines the two half planes, half spaces that are joined by this interface. So 1 on both sides. For practical reasons, you actually may want to have -1 because you want to be separated as much as possible. You want to have some margin there, just like a neutral zone that no points lie there. But it will be too strong of an assumption to make at this point that there is actually a strip completely lacking any points. So we will just assume 1, just a separation. Either way, this assumption, this condition is just an intersect in W. If you think about W, it's just an intersection of half spaces. Each condition defines the subspace in which W must lie, and so we have n of them. So maybe it looks something like this. Each condition defines some subspace like this, and eventually we would like W to lie in all of them, like here. Okay, can you find that? Well, assuming that it is non-empty, yeah, sure. This is the linear program. It's actually a convex and linear. It's a convex program, obviously, because everything is convex. And it is a linear. You can set up this as a linear program. linear for technical reasons, feasibility, linear feasibility, because we're not optimizing here. If you don't know what it is, it's fine. Linear program. Set it up like that, which means that it is computable, it's tractable. Just put it in some Python library, put it in the computer, and it will give you the answer. It will spit out W if it exists. Once we solved that problem, once we find W as above, we are ready to make prediction. Predictions of the new cells, the diagnosis. The diagnosis machine is now complete. For any new cell, let's say X, RD, we can diagnose it. So our diagnostic machine would output 1, which is cancer, if what? If the point lies on the cancerous side. So if this is greater than W, greater than 1, and -1, which is no cancer, if Wx is less than 1. Give me a second, sorry. Yeah, good. Okay, that's our machine. Maybe let's write this compactly again in one equation. We look at Wx, we compare it with 1, and then we take the sine of that. So sine of this. Perfect. Our machine is built. That's it. So far, so good. Okay, so what we described is an elementary version of a support vector machine. That's what it's called, support vector machine, or SVM, one of the basic algorithms in machine learning that is still popular. So that completes the story about the SVM. But let me ask you, do you have any questions about this procedure, the terminology, anything? Good, clear? Okay. So this all works if the data are like this, if the data are actually linearly separable. So this is a super strong assumption, never happens in practice, right? So obviously, there are sometimes points on different sides, and if there is no linear separation, what if there is like a separation that's non-linear? You know? And if they're not linearly separated, what does the algorithm do? It would just fail. It would just say there is no W with it, and that's not good. So we will address these questions one by one. So first, what if there is no linear separation? What if the data, for example, are like this? Let's say like this. There is no cancerous cells, no cancer. And this is cancer. And I'm making it up. It doesn't respond to cancer, but really something like that. No linear separation, obviously. I can't really. It's clear that no matter what hyperplane I choose, I can't separate blue from red, cancer from non-cancer. Okay. On the other hand, if you look at this picture, there is some separation, clearly. Not linear, maybe, but like that, maybe. They're kind of separated, only non-linearly. And how do you build a machine that separates them like this? there are two methods, two ways of thinking even about this. One way of thinking is, all right, it's not separated by linear, but it's separated by, let's say, circles, maybe quadratic surfaces, right? So instead of making a linear model, which involves the linear products like this Wx, let's include nonlinear, let's include quadratic terms there. So let's just build a quadratic function in X and then find it. Possible, but it becomes difficult. It becomes difficult because then you're intersecting this quadratic surfaces, and that's difficult. It's a quadratic program, and it's not clear when it has a solution, and when it does, whether it converges and so on. So that's one avenue. The other avenue that I would like to show you is kind of more elegant and practically more appealing. Do not try to build a more complicated model. So do not try to find a different separation, but transform the data in such a way that it will be linearly separated, and then solve the linear program. So we would like to transform the data so it becomes linearly separable. Just build this map phi. And it's actually obvious in this picture. It's actually obvious how to do this. Imagine you curve a little bit. You curve the space, the plane into the third dimension, so that these blue points become on the top, like near the North Pole. Then you can definitely separate them by a meridian. Meridian? Parallel? So this is the picture. If I may just put the points on the sphere in 3 dimensions. So from RD, well, it's dimension D. So from 2 dimension D plus 1, let's say, put it on the sphere of dimension 1 higher, and then hopefully these points will land like that. On the sphere, and then we can separate them using a linear method. We can separate them just like this. Transform the data. So this data, the new data on the right, is linearly separable. So we can proceed as before. Just repeat the steps before for the data in dimension D plus 1 and separate them linearly. Okay, is the idea clear? Cool. So this phi is called, the transformation is called the feature map. Machine learning people like terminology. There's a lot of terminology. Feature map, and our D plus 1, it's called the feature space. So we map this from the original space, from the data space into a new space, into the feature space, in order to make it linearly separable. We can do this in many ways. For example, we can use the stereographic projection. Stereographic projection, it projects the points from the space like this onto the sphere, but just contracting them to the sphere. So this is X and this is phi of X. This is 0. Good. Any questions? Okay. All right. Well, if I was looking at this, say, okay, this is custom made situation. I just made this very nice picture again. Okay, I made this baby picture where they're linearly separated, right? And then I made this baby picture where they're separated by circle, and I solved it. And what if they're not separated by circle, but something else? For example, what if the data is like this, which is more common scenario, even perfectly separated, but not by some like circle. So what if the data is maybe like this, like two snakes that hug each other, something like that. Okay. Then probably we can say, well, there is some separation there. We hope to do something like this. But it's neither linear nor quadratic anymore. In this case, we can say, okay, then let's work harder. Let's not project on the sphere, but project onto something else. But how do we know what we want to project onto? If we just see that the data is just a matrix. How do we know what to choose? How do we find the feature map and feature space phi into which we embed? Okay, is the setup clear? The problem clear? Everything is good? You're a little quiet today, so I'm just trying to understand it. Okay. Okay, so how do you find this transformation, the feature map generally? And the amazing idea, the beautiful idea in machine learning is that there is no need to do that. We won't, actually. We will solve this problem implicitly without explicitly finding phi. And this is how. This is a very elegant idea. It's called the kernel trick that I'll explain now. The big idea is this: rewrite everything, to rewrite all this algorithm that you have in terms of the inner products between the data, xi, xj. Suppose you can do that. So you replace inner products. Okay. Then what you do is, suppose there is some nice embedding somewhere which we do not know. That embedding essentially creates a new inner product, the inner product that is phi of x, phi of y. So after the embedding. And think of phi of x, phi of y as the original kind of inner product on the original space. So instead of thinking about phi, how to find this map phi, think about how to find a good inner product on the original space. Maybe not linear, just some function. Just change the inner product to something that you like on the original space. Then maybe it is realized by some phi. And that is exactly the idea of the proof of Grothendieck identity, in fact, inequality. Remember how we had to fight with the sign of inner product UV, and we're trying to realize it as an inner product. We find this map by tensor calculus, and it is difficult, right? The map itself is not telling us anything. But the point is that we can realize this thing as an inner product. That's it. So that is the idea of the inner trick, to never find phi explicitly, but only work with the inner product. Okay, now let's realize this idea on this example, on our example. So we would like to rewrite the learning algorithm that we already have, the linear learning algorithm, in terms of inner products. between the data points. Okay, what is our algorithm again? Let's see. Our algorithm is to find this vector. Let me actually copy this. Copy. Paste. This is algorithm, and this is prediction. Let me get to the prediction. And the prediction is this. Come on. You can do it. Copy. Paste. All right, this was our algorithm that I just copied. Let's try to rewrite it using inner products. We would like the algorithm consists again of finding W satisfying these inequalities. First of all, without loss of generality, I assume that W is in the linear span of the data. Just remember what W is. W defines the separation like this. So it makes sense that this vector W is pointing in just lying in the plane that contains the data. It won't make any sense for W to be orthogonal to it, for example. W should lie in the plane that contains the data. So without loss of generality, I can just think that W is a linear combination of the data points. Then Wxi becomes by linearity, becomes alpha j xi xj. Good, that's what we wanted to see. There is inner product, perfect. So the algorithm, when we rewrite this, becomes this. Find not W, but the coefficients that define W. So that, okay, Wxi. So Wxi, that's this, times Y. I'm rewriting this now. Wxi, Yi. So this is Yi alpha j da xi xj is greater than 1 for any I. And the prediction of the algorithm then for a new cell, does it have cancer or not, is the sign. How do we do this? Wx minus 1, and W is this. So I'm again expanding the W here. The sum alpha j x xj. Okay, I did nothing here. So, there is no method. Just substitute W, that's a sum, a linear combination into this, the same algorithm. It's still a linear program. Everything is still linear now in alpha, so there's just changed variables. Okay, so now suppose we had this embed. Suppose we know what embedding is. So after embedding, after the embedding of the feature space, after the transformation, the feature map, xi, the data, become phi of xi. So the algorithm, the new algorithm in the transformed space becomes this find alpha j. I'm just rewriting, but replacing the data with the transformed versions. So phi of xi, phi of xj. Prediction, sign, alpha j, phi of x, phi of xj. Okay. Okay, again, nothing happened. I just did the same job only in the transform space. I replaced xi's by phi of xi's. And now the crucial point. The crucial point is that now the algorithm depends only on the inner product like this between phi of x and phi of y. And instead of choosing this inner product, instead of choosing the map phi, we could choose the correct inner, the good inner product. So let's denote k of xy, this inner product, phi of x, phi of y. This is called the kernel, a kernel. And then the algorithm, okay, I'll rewriting it the third time, just with a new notation. Find alpha j. I'll be very thorough the first time we do this. K of xi, xj is greater than 1. And the prediction is the sign of some alpha j, k of x, xj. Okay. It's still a linear program in alphas. Everything is linear in alpha. Okay. And now what we do is we say, okay, let's forget about phi now. Forget about finding this feature map phi. Just take a nice function that you like the best. Okay. Just choose a nice kernel. So forget phi. Instead, choose a suitable kernel, k of xy, and solve this problem. For example, k of xy, I'm just guessing, but for example, this is a standard one. If you don't know how to find kernels, use this one. X minus y exponential x minus y squared over 2 sigma squared, like this. This is the concrete example, and that's called the radial basis function, or RBF, radial basis function kernel. So choose this kernel, this very specific one, solve this problem above. And that's it. And don't even think about phi anymore. And it's still a linear. The beauty of this is that it's still a linear program. We're making a very, very nonlinear transformation. We don't need to know that transformation. We don't even need to guess it. And we're solving the linear program. It's like, it works like a miracle. It's magic. Of course, we need to make sure that there exists phi that gives rise to this kernel, right? It's not true that for any phi there exists something like this. But we don't need to know it. We don't need to know phi. We just need to use the kernel itself. What we described is called the kernel SVM, the kernel's a simpler version of the kernel support vector machine. That one is actually very, very powerful method. Why this kernel? What's so good about this? Looks funny. Looks like Gaussian something. Why is it so popular? It's actually a default choice in some libraries. What's so good about it? Let's see. Where does this? So you can show that it's a valid kernel. There exists actually a transformation corresponding to it, the feature map corresponding to it. But let's see, where does it map? Let's say any point in RD. Let's look at the norm phi of x. Where does this point is mapped? So that's well, that's inner product of phi of x with itself, which is k of x. And if we substitute x and x, you get 0. You exponentiate 0, you get 1. Yeah, so what does that mean? It means that all the vectors are mapped to unit vectors, and unit vectors form the sphere. So this map maps RD to the sphere. It's like a stereographic projection, only better. So all these points now are mapped into the sphere. This is what we did in the first place. In the first example, where we suggested to move the data onto the sphere to curve this, to curve the data, introduce a curvature, and that will become linearly separated. But that was a kind of a custom-based solution. Now we have a general solution with just a general kernel. That's it. So the summary of this is that we can do this for pretty much any algorithm, any learning algorithm. And this method is called kernelizing a machine learning algorithm. First, you express in terms of the linear of inner products. Between the points, the data points. Second, we replace all instances of this inner product by a kernel, by k of x, y, for a suitable choice of the kernel. Okay. And if we do not know what a suitable choice of the kernel, we can start with radial basis function. That'll be it. It's a general recipe of making algorithms that are suitable for linear data work for the nonlinear data, kernelizing, without increasing the complexity of the algorithm, which is the most beautiful thing.
May I ask a question?
Yeah, go ahead, of course.
So, for example, this radial-based function, right? So, what curves does it actually produce when we are trying to look at the data in the original space? So, will it be circles or?
No, not only circles. No, it's not like stereographic. It's much more complicated than just kind of stereographic projection onto the sphere or just curving like this. The answer is I do not know how to characterize these curves, but I can give you an example. So something like this is done with Gaussian radial basis function. Pretty smooth and pretty good, right? Yeah, yeah. This is a cool plot. Yeah,
okay, and can I how do we even produce any kernels? So, for example, if I want that my data needs to be separated, for example, by sine waves or something, how can I even start to think about what form of a kernel?
How do you choose a kernel, right?
Yeah.
Well, first of all, you don't. when we have the data, usually we are totally blind. Like we have this data and it's a huge matrix. What do we see from that matrix? We don't know how this data is separate, whether it is separated, for example. We don't know that. So in this, under the zero knowledge, we, let's say, start using Gaussian radial basis curve, this one. And if it doesn't produce good results, I would suggest to play with other types of kernels. Each of them, and you can look at the chats like in machine learning. How is this kernel good? Is this kernel good? They're talking about what kernels are more robust to outliers, what kernels are produce better results for this and that. They have advantages and disadvantages, but this is like a way. I think this is like a general way to go kernel. If it doesn't work, then you start thinking about something else. For example, if this behaves funky, then you can instead of the Gaussian here, just take, like, don't take the square, just norm of x minus y. It will maybe be more robust, but it will produce a little bit strange surfaces. So yeah, there is no general recipe for that.
Okay, so there is just a, for example, like a list of kernels. I'd say it's a long one, I guess, with some variations to it, but there is no like way if you want to separate your data by curves of exactly this type. So if you want only like polynomials of degree 5, for example, there is no kernel for that.
I see what you mean. Yeah. If you want only polynomials of degree 5, then you use polynomials of degree 5, I guess, for that kernel. So for example, this is a kernel too, right? X, Y to the 5. Is it a kernel? Yeah, it's a kernel because it's by the kernel trick. X tensor X. Okay, let me get degree 3 so we don't have too much notation here. Y, Y, Y. So this is our f of x, just like in the last lecture. And like in the last lecture, we actually showed that any polynomial with non-negative coefficients can be, let's say, of degree 3, can be realized like this, can be realized to the kernel. And then you have polynomials of degree 5 or degree 3. What would be though your reasoning to use polynomials of degree 5 or fixed degree? Why would you want to do that, Maxim?
To be honest, my question is because I was like looking in this in other math topic, and from that arises an idea to separate two sets by the exact type of functions. And it's not like I want to separate them however I want, just with the given set of functions that I have. And I have never heard of this kernel trick, so I thought maybe it can be like a very huge thing to research for me. So
yeah, absolutely. You should, I think you should start there, and then if you have satisfactory answers there, then you should go elsewhere. But this is a good starting point. I think the kernel trick is a good starting point. It's a very, very powerful thing. The common polynomial kernel is this 1 plus xy to the power d, for example. This is in the library, like already, I don't know, in Python and MATLAB. This is the list of like 7 most popular kernels, and it can realize polynomial curves. What I think this, it's actually, you're raising a very good question. I think you don't want arbitrarily complex interfaces, and you don't want them because, let me show you the example. Maybe it's a good thing that we discuss it now as opposed to later. So for example, if the data is like this, what you don't want to do is to find a very complicated surface that would do something like this. Well, I should do it faster, sorry, mate. So, okay, like this, like that, okay. Maybe make it more dramatic here. Okay. I want to separate this outliers here. Like that. You don't want to do that because it makes a terrible diagnostic tool. It's a diagnostic tool that tries to adapt itself to the outliers. And you don't want to adapt the tool to the outliers. You want the tool to recognize the outliers as such and then ignore them. So what you want to do as a tool is probably you want to do something like, no, what would be the best thing here? I don't know, something like this would be good, I think, like that. So a simpler surface that understands that there will be some little bit outliers here and there, but it is still a simpler surface. So this problem is called the overfitting. You do not want to overfit the data because you will be chasing the outliers, the bad points. And for that reason, the good solution is like one you suggested, is to use a class of simpler surfaces. Let's say surfaces of degree 3. Let's say, right? They will not be very, very complicated. They will not overfit the data. Surfaces of degree 3 will be pretty smooth, let's say. Okay, so that is one of the reasons why we would like to have kernels that are not overly complicated. And that's possible. Using, for example, this. Radial basis kernel, this one. Okay, I'm not a practitioner, but I believe the role of sigma here is the complexity of this. It kind of quantifies the complexity of the surface. If sigma is too, let me think, if sigma is too small, I think, yeah, if sigma is too small, it's a very peaky thing. So it's mostly 0, it's only one thing, one big peak. And that would lead to overfitting. It would just try to adapt to very little windows of the data, capture each locality of the data individually. It will be very complicated. If sigma is too large, on the other hand, I think I'm correct here. If sigma is too large, then it produces very smooth surface, but it could miss the outliers. So that is always a trade-off between overfitting and the accuracy of prediction. So the degree of the polynomial that you are talking about, like 3 or 5, corresponds to the sigma, I think, in the Gaussian radial basis kernel, choosing the sigma as a parameter. But any other questions? Okay, cool. So here's our next thing, what we will do next, and this is kind of also a warning because some of you may want to implement this, and it will not work definitely because it's based on the exact separation. We're still assuming that the points are exactly separated by a polynomial surface, by whatever, but still exactly separated. So here's what happens next. First, we will decide which kernels are possible at all and which kernels are not. Not all functions are possible. So for example, k of x must be positive, clearly, right? Because it's an inner product with itself. So there are some conditions definitely that the kernel must satisfy. You cannot just throw any function there. That will describe the popular kernels. So that is called the Mercer condition. Then I'll explain the modern approaches to this problem, which allow for misclassification, so for outliers. The modern approach is based on optimization, introducing the loss function and minimizing the loss function for that. And that would be it. Yeah. That'll be on Monday. Any questions now? No, we're good.
I have one small question.
Yeah, go ahead,
So
Maxime.
where do you know like a good book to read about the exact separation? Or no one studies this because everyone is used to outliers.
Yeah, exactly. Okay, I do not know a good book to read the exact separation, but I know how to. I know the keyword that you may look at. Historically, the exact separation was first addressed, and the first method to do this was perceptron. Perceptron is the method that just we described. The problem is the same. We want to separate these things, and you have this W, and it's extremely simple algorithm. No optimization there. So you look at W, you guess some W first, and then you check if it is correct or not. And suppose we have this situation. Suppose I have some point, let's say it's 0.7, where I miss. So it's less than 0, but it should be positive, but Y7 is 1. So it's a cancerous point, and we classify it as non-cancerous, less than. Yeah, okay, let's less than 1. Yeah, so it's non-cancerous point. And, sorry, it is cancerous point, but we misclassified. So what do we do? Well, W has a little bit of it underperforms on X7. So what I do is I add X7 to W directly and call this new W. Of course, it increases the value on X7. The value of W increases on X7, so maybe now it performs better. And then I just repeat. I go over the points, I find the misclassification, and if it's the opposite situation, you know what if there is opposite situation, if this is positive, but it should be negative, we subtract the point. So if there is any misclassification, we either add that direction or we subtract that direction. That's perceptron. And it works if the points are exactly separated. And if you Google up perceptron analysis, it's like a half-page analysis that it actually works. So this is an exact method for exact separation. It works perfectly well. It is actually, if I'm not mistaken, it's one of the first algorithms ever implemented, machine learning algorithms. It was implemented by Mark I machine that is huge, and one of the first, or maybe the first computer. But now we have this problem with outliers, and we have the problem of nonlinearity. In fact, the perceptron itself can be easily kernelized because it just defined using inner products. So just do what we did. We can do kernel perceptron easily. But modern approach to this is using optimization, just like we're trying to describe in support vector machines, and it works better in the presence of outliers.
Okay, thank you very much.
You're welcome, Maxim. Any other questions? Good. Okay, I'll stay a little bit here if you need me. In case anyone has questions, any questions about homework, anything else. And then I will send out an announcement about the new meeting. And you have a wonderful weekend and stay safe. Stop recording.